Hello everyone. In this section, I will describe some mistakes you may made when describe combination logic circuit, especially you are a beginner. The first mistake is incomplete sensitive list. Let's see the code below. So you can see C is missing, okay, in the sensitive list. So what's the bad effect of this code? This will cause the function of alter and the get level list list don't match. Why? At alter simulation, the value change of C will not cause the trigger of this block. Yes, that is the value change. For example, C change from 0 to 10 will not cause the execution of this code, and the value of out 1 will not change, will not update. While after synthesis, C must be an input of the combination logic. Yes. Yes. So after synthesis, C must be the input of this combination logic, and the value change of C must cause the value change of out 1. So the function of alter simulation and get level simulation will not match. This is a problem. Okay, the second is incomplete if-else or case item. That is, you write if or else if, but no else paired with it. Or you write a case statement, but there is incomplete match items and without the default branch. So I have said before, this will cause latch. Yeah, such as the code below. This will cause latch. This item is missed. Can you figure out, after synthesis, the circuit diagram? What's the circuit diagram? Can you draw a circuit diagram for this code after synthesis? Think about it. Okay, you can pause the video. This is my answer. This will generate something like that. This is a latch, okay? Level sensitive. So when s equal to 3, after the inverter, this is 0. So the value on this marks can't pass through this latch, okay? So the output value of y will keep the last value. Yes. When s not equal to 3, okay, this point change to 1 to 0, and this change to 1. Then s will select the input, and the value here can pass through to the output of latch. So this is the diagram after synthesis. And what's the problem? Function is the same, and why latch is not allowed at this place? Why? Okay, this is because usually we need the enable pin of latch connected to a signal coded clock. That is a signal with fixed period and is glitch free. Yeah, the important glitch free. Okay. So it's a period signal, and it can't have glitch such as something like that or something like that. Yeah. So if you just click the enable pin of latch to the compilation logic output, there may glitch at this point. For why there is glitch at the output of compilation logic, you can Google it. If you don't know, okay, if you can't find the answer, you can post this question, and I will reply to you. And for why the enable pin of latch can't have glitch. Okay, this is the problem of static timing analysis. Okay, I will explain static timing analysis in part 4 or part 5 of this course. Okay, and this time you just remember the latch generated by a compilation logic always block is not allowed. Okay. So how to avoid latch? If you have some complex code and there is many case match items, yes, and you have to describe many output signals. So it will be complex at coding if you have to write every output signal and this if statement, and you have to write the else. Yes, you have to write the else branch pair with the if branch. So this will cause a lot of coding effort. How to avoid this? Verilog gives you a simple way of deal with it. You just give the default value to all the output signals, and the head of the compilation logic always block. So this is the default value. Okay. This is the default value for all the output signals this always block will generate. So you just assign a default value to the output signals of this always block. Then in the code below, you can just update the signals that may change value for this situation or for this branch. So let's take this segment for example. For this segment, we have just updated one signal. So the default value will be automatically right here. Yeah. Or you can understand it as your default value has been automatically copied here. Yes. So you have copied here, and it will give you an else branch. And copy all the default values again to here. And this is the behavior of this syntax. So after this, all the case and the if-else statement will be complete. Okay. So this is a useful syntax that can ease your coding effort. And for the last For the last, okay, it's the same. It will the behavior of the syntax copy the serialize to here automatically. Okay. Okay, the third problem is combination logic loop. Combination logic loop. So read the code below for several seconds or 1 minute. Take care of the signal A. If you have understood the function of this code, can you draw the circuit diagram of this code? Yeah, is that something like that? So there is a loop for signal A. Yes, you can think it like that. When cell is 1, okay, when cell is 1, what's the behavior of this code? A value will be passed here, and we assume C is 1, also 1. Okay, so A will be and 1. Yes. So we assume the beginning value of A is 0. So A will equal to 1 and fade back to this point and change it to 1. 1 will be passed to here and again generate 2. 2 will be fed back to here and again generate 3. So as you can see, this is the endless loop. Okay. So from the view of Verilog language, it's a sensitive triggered. Sorry, it's an event trigger language. Yes, it's an event trigger language. So you can say when cell is 1 and there is a trigger, there is value change and at A. So this block will be triggered. Yes. This always block will be triggered and cause this signal updated. This signal updated will trigger this assignment. So then the value of A will be updated again, then trigger this block, then trigger this signal. So this is an endless loop. The same as the function in the circuit diagram. So this will cause the simulator halted. This simulator can't end this loop. Yeah. So the simulation time can't go forward. You can say the simulation time will be stuck at 10 nanosecond or some other time. It can't go forward. It can't increase the time to 11 nanosecond. Yeah. So sometimes if you say your simulation is halted and the simulation time doesn't go forward, you have to check whether there is combination logic loop in your design. And the fourth is multi-driven. So please say the code for code segment here. Yeah, so this is the multi-drive point. Yes. Either though underline MAC, this signal is assigned value in two different always blocks. So the synthesis tool will think it. There is two logic clone will drive the same point or will drive the same load. Something like that. Okay. The first logic zone that will drive this point, and the second logic zone that will drive the same point. This is called multi-driven, and this is not allowed in our digital circuit. So even if you have used the enable signal to identify that the multi-driven can't happen, and you think this is actually a max, yes, you can max it between this value and this value, but the synthesis tool can't understand it. You have to write it clearly in your code. Okay, you have to write it clearly in your code and assign the value to this signal only in one always block, and this code will generate a circuit, something like that. So for each wire signal, you can only assign value to it and assign statement. You can't assign it twice or third times. And for a rig signal, you can only assign value to it at a single always block, not two, not three. Okay. Okay, and the diagram here may wrong. Okay. Actually, it may be something like that. Okay. Yes. Yeah. That's the DFF. That's it. Maybe something like that. Okay. Yeah. Okay. Okay. So are you nervous now? You may make some mistake in your code. And are you afraid of writing artificial code now? Just take it easy. All the 4 mistakes I have explained can be checked by the Lint tool. Okay. So take it easy. The tool will help you. It will find the problems for you. So what's the function of the Lint tool? It usually will check whether the artificial code is synthesizable or not. And it will check your coding style and make sure the function equivalence between RTL and git level let list. And it will check the potential problems in your artificial code, such as the problems I have mentioned before. Okay, and for some tools, it also has some advanced features, such as it will check the clock domain cross architecture. That is, it will check your circuit architecture is correct or not for clock domain cross point. That is, the tool will check whether your digital circuit is correct at the clock domain cross point. So what is CDC? I will explain it in this part 3 of this course. Okay, part 3 actually is commonly used hardware architectures. I will explain these commonly used architectures at part 3. Oh, one more point. What's the tool you can use? Spyglass. Yeah, Spyglass from Synopsys is a Lint tool. And also Cadence may have its Lint tool. Well, I didn't find any free Lint tools for use, so this will be charged. Okay, that's all for this section. Thanks for watching.